Okay, this is Chapter 17, Lesson 1, and we're going to talk about thermochemistry. We talked a little bit about this in the fall. We did a little bit with thermochem and Hess's Law 1 and the heat calculations. And now in this unit, we're going to focus more on spontaneity and entropy and the law of thermodynamics and free energy. So let's talk about what spontaneity and entropy means. And for that matter, let's talk about what thermodynamics means. You know that thermo means heat, right? And then dynamics, what does that refer to? So thermo is heat, and we know that heat is energy, and dynamics is how things move. So we're really going to be talking about the flow of energy. And one of the things that you have to realize when we talk about the flow of energy is you need to make sure that you know what perspective that you're looking at that flow from. Is it from a systems point of view or a surroundings point of view? So spontaneity means spontaneous, meaning happening by itself. Entropy is randomness. So what will make all things happen? We know that we need low energy. So when we talk about low energy, we're really talking about enthalpy. And that is delta H. And we're talking about more disorder. So we want more disorder. And that's entropy. So what type of conditions are going to give us low energy and more disorder? In most cases, that's exothermic and increasing our entropy, going from more ordered to less ordered. All right, so entropy, as I've been saying, is randomness or disorder. Okay, so remember that solids have less entropy than liquids and have less entropy than gases. Entropy is going to be delta S, and enthalpy is going to be delta H. Okay, so now we're going to look at microstates. What happens when we go from a closed system to an open system? And this actually has to do with statistics and something called positional favorability. So let's imagine that we open these closed valves, okay? And all of these are letters, different letters of gases, A, B, C, and D. And what do we know is going to happen? Well, we know eventually that 50% will wind up on both sides of the flask. But how that 50% arranges itself has to do with positional favorability. So given the 4 different gases that are in the flask, you can see that arrangement 1 might be A, B, C, and D all on the left side. Or if you look at 5, we could have the reverse of that, A, B, C, and D all on the right. Well, that neither one of those are probably favorable, right? In arrangement B, we have B, D, and C on the left and A on the right. And then we change out each one of those, where B would be isolated, C would be isolated, and D would be isolated. Okay? But again, not the most favorable situation because you have 3 on one side and 1 on the other. In 4, we have the actual opposite of 2. And then in arrangement 3, we have 2 and 2. And we have a possible of 6 different combinations of what could happen. So the most favorable state is the one that is most spread out, which would be arrangement 3. Okay, so let's look at the thermodynamic laws. The first law is the law of conservation of energy. You're already familiar with this law. Energy can't be created or destroyed, but it can change from one form to another. Another principle that we need to review, and you already know this, is that heat flows from high to low, never in the reverse. The second law says that systems have an overall tendency to increase the entropy. So an example of this could be boiling water. We're going from a liquid to a gas. Volume increases, therefore delta S, or entropy, increases. We can also think of this as sublimation of carbon dioxide, going from a solid directly to a gas. We can say that this happens when we put magnesium metal in hydrochloric acid. There are lots of situations where we can give examples of entropy increasing. All right, next we're going to talk about free energy, and that's delta G, and that's actually Gibbs free energy. This is delta G, and that is Gibbs free energy. And that's the amount of energy that's available to do work. You may have talked about this in physics. And one of the formulas that's going to be most important is delta G equals delta H minus T delta S. So the change in free energy is equal to the change in enthalpy minus the temperature times delta S. And you have to remember that T is in Kelvin. That's one thing that you have to remember here. Again, like I said, you need to be aware of what the system and the surroundings are. The easiest way to figure out what's happening in this chart, and this is probably one of the most important charts, or both of these on this page, in understanding what's going on in this unit. So let's think about delta H. When delta H is positive, that means that it is endothermic. And if it's endothermic, that means that my spontaneity is also going to be positive, which means more disorder. Now, if delta G is positive, that means that the reaction is non-spontaneous. And that means that work is done on the system.
Set the microwave sponge on high for 2 minutes.
Okay, what about if delta H is negative? Well, you know that it's exothermic, okay? If our delta S is negative, then that means it's going to be more ordered. And if delta G is negative, that means that the reaction is spontaneous. Okay. Now, we have a special case, and that's when delta G is equal to 0. If delta G, or free energy, is equal to 0, then that should tell us that our system is at equilibrium. Then the equation has to change. So the equation that we would use then, if delta G is equal to 0, is delta G equals negative RT ln of K. And both of these are in your reference tables. And what you have to remember here is that R is 8.3145 joules per Kelvin dot mole, because we're talking about energy. Okay, so we can't use R, the gas law constant. We need the one with joules in it. Now, the other thing that I want to point out is that when we talk about these problems, is that often our delta H may be given in kilojoules. So we're going to have to make sure that we have agreement of units. And in most cases, it's easier to convert kilojoules to joules, because your delta G is going to be in kilojoules. So the units for your delta G are going to be in kilojoules. So let's convert kilojoules to joules. And then if you need to report it in a certain unit, you can always convert it back. All right, so in this problem, what is the boiling point of a solution where the delta H of vaporization is 23.5 kilojoules per mole and the delta S is 34.5 joules per mole dot Kelvin? Well, the first thing I realize is that I do not have agreement of units. So what we have going on here is we have phase equilibrium at the boiling point. So we've got some substance, and it is going back and forth between liquid and gas. All right, so we've got 0 equals delta H minus T delta S. So when we rearrange the formula, we're going to get T equal to delta H divided by delta S. So my delta H is 23.5 kilojoules per mole, so that's going to be 23,500 joules per mole, divided by 34.5 joules per mole, and I'm going to get 681 Kelvin, which is also equal to 408 degrees Celsius. Another thing that's important to remember is that you have an element in its free standard state, then our delta H is equal to 0. And we use that when we use the appendix at the back of the book. So just a couple examples. If I have F2 gas, then my delta H is going to be equal to 0. if I have Hg liquid, then my delta H is going to be equal to 0. But obviously if I have ammonia gas, which is NH3, which is a compound, then it wouldn't be 0. Okay, I'm going to continue this chart on the next page because I need room to write. So I'm going to number these 1, 2, 3, and 4 so that it's easier for me to talk about them down below. We're going to take them one at a time. So let's figure out what's happening. Let's say that delta H is positive. So that means that it's going to be endo. And delta S is positive, which means more disorder. And you get a question, and they want to know whether or not this is spontaneous or not. Well, the easiest way to do this is to write your formula and figure out what's happening. If this is positive, delta H, and this is positive, okay, and let's say this is big and this is small, then what is going to happen to delta G? Well, in this type of situation, if you put the math in, you can see that if T is positive, right, or you can see that this is going to be dependent on temperature. So let's say T is positive. Well, if T is big, then what is delta H going to be? If T is big, right, then my delta H is going to wind up being negative, which means that it would be spontaneous. So when we talk about delta G and spontaneous, we can say that delta G can be either, for this one, either positive or negative, okay? However, it will only be spontaneous at high temperatures. All right, let's look at a different one. Let's say delta H is negative. Well, you know that it's exothermic. And let's say that delta S is negative. So now you have more order. Is this going to be spontaneous? Again, we have to look at the equation. Look at it from a mathematical standpoint. So now I'm saying that this is negative, and it's big, and we're saying that this is negative, and it's small, okay? What we know about temperature. We know that this has to be small. So again, this is either going to be positive or negative, but it will only be spontaneous at low temperatures. Only at low temperatures. All right, let's look at number 3. If this is endo and delta S is negative, so that means order. So here it doesn't matter what's going to happen. If the equation, if delta H is positive and delta S is negative, then delta G is going to be positive, and this is going to be non-spontaneous. It does not matter what temperature is. And if our reaction is exothermic and we increase entropy, then it doesn't matter what the temperature is, it's always going to be spontaneous, and delta G will be negative. Remember that the universe favors a negative delta H, meaning low energy, and a positive delta S, meaning high entropy. And I will leave you with that thought. And that is the first lesson. There's only one more lesson in this unit. Pretty easy stuff. All right, have a good night.